Good morning. My name is Kaushik, and today my topic in advanced databases is about optimized management of large-scale data sets stored on tertiary storage systems. So, coming to the introduction, smart management of large-scale data sets in tertiary storage systems begin by combining the effect, retrieval, and dataset manipulation capabilities of a multidimensional array DVMS with the huge storage capacity of tertiary storage media such as magnetic tape. This DBMS must be extendable with easy-to-use functionalities to automatically store and retrieve data to and from tertiary storage systems without user interaction. The Bavarian Research Center for Knowledge-Based Systems designed RSDAMAN for generic multidimensional array data of arbitrary size and dimensionality. By generic, we mean that functionality and architecture are not tied to particular application areas. Figure depicts the extended Ras-Daman systems architecture with tertiary storage connection. The original Ras-Daman architecture included a client, a server, and an underlying conventional DBMS, such as Oracle, that served as a storage and transaction manager. Efficient storage of large multidimensional data. An MDD object includes an array of cells of some base type integer, float, or arbitrary complex types located on a regular multidimensional grid. An often discussed approach is to chunk or tile large data sets. This approach is common for multidimensional arrays in different application areas. Basically, chunking means subdividing multidimensional arrays into disjoint subarrays. All chunks have the same shape, size, and dimensionality, and therefore align. Tiling is more general than chunking because it does not require that subarrays be aligned or have the same size. Ras-Daman allows subdividing MDD into regular or arbitrary tiles. Data export to tertiary storage media. We must distinguish two possibilities for storing data in Ras-Daman. First, we must explicitly store data on hard disks in the underlying DBMS. This is useful if the data access time is critical. For example, if some users require frequent access to the datasets. After several months, if the datasets are less important, these users can use the query language to export them. To allow such exporting, we integrated a new statement into Ras-Daman's query language, that is, export from object where condition. The second possibility for storing data is to export datasets automatically and independent of user interaction to tertiary storage media. So coming to the data retrieval, we can distinguish three well-defined areas regarding data accessibility, which are online, nearline, and offline. Online access means datasets are stored on hard disks, so access time is very fast. Nearline access means datasets are stored on magnetic tape integrated in robot controlled libraries. Access is far slower than with online access, but data retrieval is automatic. Offline access means datasets, for example, backed up or rarely used data, are stored on magnetic tapes which are not integrated in robot controlled libraries. In this case, retrieving datasets requires user interaction. Before someone can request such data, the HSM system administrator must catch the magnetic tape and put it manually into HSM system. Techniques for reducing tertiary storage access time. So first one is super tile concept. So here in the Ras-Daman DBMS, the tiles are the smallest data access unit. So their range is 64 kilobytes to 1 megabyte, and they are optimized for hard disk access. This is far too small for data sets that are being held on tertiary storage media. So we must use different granularities for the hard disk and tape access because they are different in their access characteristics. So the second one is clustering. So for tertiary storage system where the device positioning time is high, the clustering is very important. The goal here is to minimize the number of search and media load operations, which will reduce the access time and reduce access time of clusters which are read from tertiary storage systems when subsets are needed. So the clustering exploits the spatial neighborhood of tiles and datasets. Clustering tiles according to spatial neighborhoods on one disk or tertiary storage system will proceed one step further in preserving spatial proximity. This is important for the typical access patterns of array data because users often request high data using range queries for which spatial neighborhood concept is suitable. The third one is caching. To reduce the expensive tertiary storage media access, we must use RAS demands underlying DBMS as a hard disk cache for data sets held on tertiary storage media. The general goal of caching tertiary storage data is to minimize the load which is expensive, and rewind and reading operations from slower storage levels like magnetic tape. The tertiary storage version of RASDMAN migrates requested data sets held on tertiary storage media to the underlying DBMS. The migrated supertiles are now cached in the DBMS. After the migration, the RASDMAN server transfers only requested tiles from the DBMS to client or application. So coming to the further techniques, we have additional techniques for reducing tertiary storage access time, including scheduling, prefetching, and input-output parallelism. Scheduling tertiary storage media access means optimizing the media read order. This optimization reduces expensive media seek and exchange operations. The focus is on scheduling policies that bundle all requests on a medium before exchanging them from robotic library loading station. Input-output parallelism is also possible because HSM systems have several read-write drives and robot arms for handling thoughts of magnetic tapes. So here is a diagram which shows the performance comparison of different retrieval scenarios. We have RASDMAN's DBMS cache, which is lying around 200 access data time in seconds. So from RASDMAN HSM cache, we have 300 to 400 seconds, which it takes. From HSM tape, we have around 1000 seconds of access time. The traditional access we have is 4044 seconds. So the conclusion is the RASDMAN's multidimensional query language can be extended using a new concept called object framing. So with this extension, we have the users will no longer be restricted to performing range queries in the shape of multidimensional hypercubes. Now they will be able to formulate range queries by indicating complex frames. Thus, object framing represents a generalization of geometric operations. Another research topic is parallel query support for multidimensional data. Thank you.